Hi, today we will learn electric field lines and we will learn how it represent electric field in magnitude and how it gives the direction of electric field also. So let us start. Okay, we omit it. Field lines. So it has to represent electric field. So let me first of all write formula of electric field. K Q upon R square R cap. So electric field has to represent both of magnitude of electric field and its direction. So let me draw some of the electric field lines so that you can understand. And one formula more I should write down here. Electric force is equal to QE. So the direction in which force is applied will be the direction of electric field also. And we have already learned that for positive charge, these lines of forces are radially outward. These lines of forces are in outward direction. What does this mean? This means that whenever you place a positive charge at any point on these lines, they will be accelerated along outward directions. Means they experience a force along this outward direction, and the direction of force is same as direction of field. So this is a very good way to represent the direction of electric field. So this is first case when we have taken a positive charge, and for that positive charge let me take a different charge here, capital Q, and here small q. So if we place any positive charge in the vicinity of or in the electric field of a given charge, then the small charge plus q will be accelerated along one direction, and that direction is the direction of force, and that actually is the direction of electric field also. So in this way the direction of electric field can be realized. Now for a negative charge you will find that, and we have learned also from before that electric field lines are radially inward. Now what does this mean? This means that if you place a positive charge here on these lines, this charge will be accelerated towards this negative charge along this direction. Means force is acting towards inward radial direction, and the direction of force is same as direction of field. So these are the two cases. Let us consider some more cases for clarity of these field lines. Suppose we have two unlike charges, and we find how the field lines are there, and these field lines will initiate from positive charge and will terminate along a curve by being along a curve to a negative charge. It means that when a positive charge is placed at any point here, then it will be moving, it will be force along this path. So this is the direction of force, and so why this is also the direction of field. Now if you place a positive charge at some other place, so it will be forced, it will be accelerating along this way. So the direction of force is same as direction of field. Let us draw some more electric field lines. So here we find that for a single positive charge, these lines are continuous up to infinity. In second case also, these lines are continuous from infinity to point charge, from infinity to the negative charge. Now in this case, we are having two unlike charges, and we see that the lines of electric field are not remain straight one, they are curved one. First thing, and second thing, that they do not extend up to infinity and they contract in size. So in this very case, we see that there is contraction lengthwise, contraction lengthwise, and this shows attraction between two unlike charges. Attraction between so we learn that how this arrow sign gives the direction of electric field in all the cases. And here in third case we find that these arrow signs are away from positive charge and these are towards negative charge. Now fourth case, if we have two positive charge only, two like charges only, either both of them are positive or both of them are negative. So let me take the two positive charges only. So when the lines of electric field extend from point charges, you will see that they do not go along a straight path, rather they are pressurized laterally, and due to pressure they take curved path. You can see here they take curved path. Along other side it is going straight way up to infinity. This side also it is going straight way up to infinity. But the lines of forces which are coming close to each other, they are laterally pressurized. This line of force, this field line, presses this field line, and due to which the line take a curved path. So when we have two like charges, then this kind of field line pattern is obtained. What does this mean? This means that when you place a positive charge at this point, it will start accelerating, it will be forced along this curved line. If the unit positive charge is placed over here, then it will be forced along this curved line. And as we know that the direction of force is same as direction of field. So this is how the direction of field at each and every point can be obtained. Here one more thing can be observed, that at the center, at this very point, there is no field line. No field line. So if field line is not here, so obviously field also is not here, and so if you place any charge at this very point, it will experience no force, no field. So it will remain in equilibrium state at this very point where there is no field lines. And this very point is called neutral point, at neutral point, charges are at equilibrium. Means they are at rest. They are at rest, or you can say in uniform state of motion, but here it is at rest. Rest or uniform velocity. Now this equilibrium is not balanced equilibrium. This equilibrium is unbalanced equilibrium. So let us understand what is the meaning of unbalanced equilibrium, and let me take some examples which is other than these points. Let me take example of two keeps. One keep is kept upside down on the ground, and other keep is kept upside up and downside down. Let me take it in notes. So these are in equilibrium, means they are standing, they are not moving. They are not moving. So when you apply force at this very key, which is upside down, what will happen? As soon as you touch it, it starts falling, and in each and every case it has to fall only. It has to fall only. But this key, which is upside up, and when you apply some force at the top of this key, you find that after moving to some distance, and as soon as you release the force, it again comes to its initial position. So this is called balanced equilibrium. Means when you release the force, the object restores its position. So this equilibrium is called balanced equilibrium. But in this very first one case, what we observe, that a slight application of a slight force makes this key fall, and in each and every case the key will fall. So this is the case of equilibrium तो है यहाँ पे, standing तो है, लेकिन such equilibrium is called unbalanced equilibrium. You can understand all this concept on the basis of potential energy also. So you know that center of mass lies close to the portion where mass is more in magnitude. So here center of mass is near to base. Center of mass is near to base. So potential energy will be mgh. Here h1 is increased. Here potential energy is more, so equilibrium is unbalanced. But in this very case, you can see that H2 is small, so potential energy mgh2 also is small. So less the potential energy, smallest the potential energy, balanced equilibrium will be there. So these are the concepts behind balanced equilibrium and unbalanced equilibrium. So let us come to our point. So I was telling that the charge is in unbalanced equilibrium. Let us see how. So suppose if this charge is forced along any one direction, it starts moving along any one direction. So there is a positive charge, like charge. So this positive charge will again restore its position because it will repel this charge. So the charge will be again restored to its initial position in this direction. Now what will happen when a force is applied in this direction? Will it start flying off, or some force is there which will restore it again over here? So we see that there is a positive charge. So like charges will repel each other. So it will be again acted upon by a repulsive force, and this will restore its position. So in two directions we find that the position is restored, but the same charge when starts moving along perpendicular direction, there is nothing there to restore which can restore its position. So in perpendicular direction, if the charge starts moving, then its position cannot be restored. So such equilibrium is unbalanced equilibrium. So these four cases we learned. Let us sum up all these four cases. The electric field lines are the lines which are in direction in which a positive unit positive charge starts moving when placed there freely. So that is the direction of electric field at that point. That is the direction of electric field at that point. So we learned what is the direction of electric field. Still we have not learned magnitude of electric field, that we have to learn. But one more thing I would like to say regarding this, that the electric field lines are away from positive charges. Radially away. This you can take as first property. Now second property. Here we must write properties of electric field lines. So electric field lines are away from positive charges. These are radially away. For negative charges, the electric field lines are radially inward. The negative charge. Okay. Now third property. I have already written. Third property is that they contract lengthwise. Which shows attraction between the charges. Unlike charging, fourth property, they exerts lateral pressure which shows repulsion between two like charges. So these are some properties. I will be discussing some more property. But before that, I would like to discuss one thing that can give idea of the magnitude of electric field too. So magnitude of electric field, let me write it again, is equal to KQ upon R square R cap. Here this part is called magnitude. So let us search a quantity, physical quantity in this picture that is representing the magnetic field lines. Is there something which can give the magnitude of electric field? So let us find, there is one quantity, line densities. Let us find it. What is line density, electric field line density? Okay. So let us take the case of lines coming outside from positive charge. As we have learned, these extend up to infinity and these are discontinuous. These are not discontinuous, these are continuous lines. It goes up to infinity. Okay. So we have to find electric field line density on a spherical surface. On this surface, what is electric field line density? Let us find. Since it is surface line density, so surface line density will be written as sigma. We have already learned these are called sigma. So surface line density will be equal to lines number of lines divided by area, and let the number of lines is equal to n divided by area of this surface. And we know that area of surface can be written in terms of its radius, and it is equal to 4 pi r square. So surface charge density comes equal to n upon 4 pi r square. Now let us compare this equation with the equation of electric field. And we find that surface charge density is inversely proportional to square of radius. Here you can see, and electric field also is inversely proportional to square of radius. And other thing is a constant. Here also we have constant 4 pi. And then one more quantity is there, charge, in case of electric field, and this surface charge density has a quantity, number of lines. So we see there is a great similarity between surface line density and electric field, because here you can compare even number of lines with charges also, because you can consider that if the number of lines will be anyhow related to charge only. So here you have charge, here you have number of lines, because this number of lines are only due to charges. So this will be anyhow, it will be related to charge also. So mathematically we find that line densities are very much similar to the magnitude of electric field. So electric field can be pictorially very clearly represented by surface line densities, and I am showing you. Suppose you have to find electric field at any point, so take unit area at that point, and suppose you have to compare electric field at some distant point. So let us compare electric field at this point and a distant point. So we see that here lines, electric field lines are denser. Two lines are going from here, and here line is not denser, it is less denser, only one line is going. So obviously the line density, electrical field line density will be more here, and a line density will be less here. So you can find that electric field is strong over here, and electric field is weak at this very place. So you compare electric field by comparing electric field lines density. So relative density of electric field lines also tell you about the strength of electric fields at that very point. You can compare in the same figure. You cannot compare in two different scenarios. As for the same charge, some other person may draw some different number of lines. For the same charge, he can draw 3 lines or 4 lines to represent electric field, and for the same charge, some other person may draw another number of field lines. So line density can be compared in the same figure. You cannot compare line density in two different scenarios, even if the charges are same. So we saw that the field line densities give the idea of electric field. One thing, so magnitude of electric field. So electric field magnitude can be had. We have some idea of magnitude by getting the field lines density. Density is more, electric field is more. Density is less, electric field is less. So magnitude is given here by electric field lines density. You can realize magnitude of electric field looking at the field line densities. If denser the field lines are, more the electric field at that very point. So magnitude can be shown very clearly, and direction we have already learned. Direction is given by the direction of arrow sign. So let me write another things. Next point, and you will sum up all these points at one place, that the magnitude of electric field is given by relative field line densities. Relative field line densities. So one more thing. Okay, next point. You will sum up all these points, fourth point, and this you can take as fifth point. Now sixth point, sixth property, that magnetic field lines do not intercept each other. Sorry, electric field lines. Do not intercept each other. For if they intersect, let me show you. So if they intersect in this way, if they intersect, there will be two directions of a single vector, and that is not possible. A vector has only one direction. So for if they intersect, there will be two directions of electric field, and that is not possible. Now next point. These field lines, these electric field lines emanate or go to any surface perpendicularly. The field lines, the electric are normal to, perpendicular to any surface. Let us prove it. Let us prove it. So, let us assume that these field lines are not incident perpendicularly. Let they are incident at some angle. Let the field lines are incident at some angle. Look here, it is incident at some angle. So it will have two directions of electric field now. If you resolve this electric field in two directions, okay, let me on a different way I will do it. So suppose electric field line is falling at some angle theta angle. So it will have two components, a perpendicular component and a normal component. So let us resolve the electric field along the two directions. Okay, let me take theta here. Let me write. Suppose angle here is theta. So here the angle will be theta. And if the electric field is E, then its component parallel to the surface will be E cos theta, and a component in the surface will be E sin theta. Now you can see we have electric field along the surface, we have electric field, and we also know that on metallic surfaces we have charges, free charges. There are free charges in metallic surfaces. So we have both electric field and charges. And we know that a force acts that is equal to QE. If charges are there, electric field is there, so obviously the charge will experience some force. The charge some force and will accelerate, constituting current. But that does not happen. Have you ever seen that without applying any source, without applying any battery, current is flowing itself? By placing an electric field, that is not possible. We have never seen a current without applying any source of electricity, without connecting battery. So, that is not possible. To have current without connecting the metallic surface to a source or a battery. Source or a battery. So our assumption that electric field lines is making some angle theta is wrong, and so it is clear that electric field lines are always normal to the surface. So our assumption that electric field line is incident at an angle theta is wrong. And so it is clear that the electric field lines falls on a surface perpendicularly. Okay. So these are some properties of electric field lines, and we saw that it very clearly and pictorially it represents electric field. When you have been given electric field lines, you can very you can have a very good idea of electric field at any point. Suppose here at this very point, in this figure, at this very point, then I will ask you where the electric field is more, here or at a further point, and you will say that no, electric field at this point is more strong, it is stronger, as the line densities, electric field line densities are more over here, and the arrow sign, this gives direction. So the electric field lines very elegantly represent electric field, and it gives idea of both magnitude of electric field and direction of electric field. Now these are some